Okay, my name is Ogoun, and I'll be presenting on nanoporous gas transport in shale reservoirs. Okay, this is the content outline, so I'll be taking briefly on the introduction, start overview, and then the aim and objective, the material and the method, the resultant discussion, the conclusion, and then further works with questions. The introduction. The increase in energy demand on a global scale has pushed the oil and gas industry into new technological advancement for the exploration and production of unconventional reservoirs. Natural gas accounts for a large percentage of this increase in the demand for energy. This has necessitated the rapid growth in the production of shale gas reservoirs in the United States of America, China, and in the Middle East. In a more conventional gas reservoirs, gas flow is simple, uncomplicated, and can be described by simple flux pressure drop expressions. But in shale reservoirs, however, this relationship takes the form of a more complex and multi-scale flow process involving spatial flow mechanisms. Shale gas reservoirs often contain a significant number of nanopores, leading to an apparent permeability that depends on the pore fluid type, the pore pressure, and the pressure differentials. The complexity of the geometry of shale reservoirs has drastically stimulated basic research on the transport mechanisms involved in the extraction of gas from shale formations. Yeah, the research aim and objective. The research is aimed at studying the gas flow through different sizes of nanocore samples by experiment and comparing with available theoretical data. The objective, the appropriate nanocore samples will be selected and characterized. A laboratory measurement of the samples will be made, and then a rig will be set up. And then flow experiments will be carried out at different pressure and temperature conditions. Then the parameters necessary to analyze the data will be determined, and then the results analyzed will be compared with the theoretical data available. The materials used for the rig setup are the pressure gauge, the pressure valve, the gas regulator, the gas cylinder, the thermometer, the thermocouple transducer, the flow meter, the heat regulator, the heat jacket, and the core holder. Yeah, this is basically the cross-section view of the membrane used for the experiment. And this is the membranes, the experimental setup. The system is heated to a desired temperature and allowed to reach thermal stability. Natural gas is then released from the gas cylinder and allowed to flow through the nanoporous core to an exit line where the gas is discharged. The pressure gauge is monitored and regulated to a desired pressure and temperature condition, after which the system is allowed to operate for a period of time for the reading in the flow meter to stabilize. Once this reading is stabilized, once the stability is attained, the reading on the flow meter are recorded. This experiment procedure was conducted for 3 different nanocore samples with pore sizes of 15 nanometer, 200 nanometer, and 6,000 nanometer at predetermined pressures of 0.2 to 3 bar. The experiment was carried out at an assumed reservoir condition of thermal stability of 100 degrees Celsius, 150 degrees Celsius, and 200 degrees Celsius for each of the 3 different core membranes. Then the readings in the flow meter were taken and all summarized here. Yeah, from the first column, the inlet and outlet pressures in bar were gotten directly from the experiment and were converted to Pascal. The pressure drop was derived from the difference of the outlet and the inlet pressure in Pascal. The average pressure was computed by adding the inlet and the outlet pressure divided by 2, and then the inverse average pressure was derived by dividing 1 and the average pressure. The flow meter readings for each of the cores at each temperature were also measured directly from the experiment using the flow meter in LPM and later converted to meters cubed per second. The surface area of each of the membranes were derived from the laboratory. The flux was calculated as a ratio of the flow rate and the surface area. And finally, the permeance was derived as a ratio of the flux and the pressure drop. Here are the results and discussion. The pressure drop was plotted against the flux, which is the rate of flow of gas per unit area, where the area is the surface area of the medium in which the gas is flowing through. From the plot, as the pressure drop increases, the gas flow also increases, confirming Dicey's law that fluid flow needs a pressure differential between points in which flow is directly proportional to the pressure gradient. This indicates that higher pressure differences will give a greater flow rate. The average pressure in these graphs, the average pressure was considered and plotted against the permeance for each of the 3 nano core samples and the 3 different temperatures. The permeance is the measure of the degree to which the core sample allow gas to permeate. From the plots, as the average pressure increases, the permeance tends to decrease, confirming other studies that apparent permeability of rock samples increases gradually with decrease of average pressure. In conclusion, gas flow characteristics in nanocores is essential to obtain parameters that can be used for accurate numerical modeling of shale gas reservoirs. The effect of the pore size on the behavior of the gas flow was analyzed, and the results obey the criteria to divide the flow stage into dicey and non-dicey flow. A mathematical model for further works, a mathematical model to characterize gas flow in nanotubes will be established, and a new formulation to compute the apparent permeability for gas flow in nanopores will be derived based on the experimental results. Additionally, the new model will be compared with others such as the Java pore solutions and other analytical solutions with the purpose of showing that the new model matched the experimental data. This work will also provide a solid foundation for further research on gas flow in shale strata and numerical simulations in nanotubes. Thank you for listening, and I'm open to any questions. Thank you.